Hello, my name is Ramon Antonio. Let me present a novel research and development direction in the area of array DBMS. Array DBMSs manage big multi-dimensional array storage, processing, and even visualization in some cases. Physical world simulations have been traditionally implemented on diverse types of grids and meshes that can be modeled as ND arrays. As multidimensional arrays are at the core of array DBMS, it is logical to apply array DBMSs to physical simulations to benefit from array DBMS capabilities. Cellular automata seem to be a good starting point for integrating simulation into array DBMS due to having multi-dimensional array models for their lattices and numerous successful applications. As an example, we focus on road traffic simulation. Road traffic simulation is used to plan road changes, optimize traffic lights, analyze throughput, integrate objects, to name a few. Traffic cellular automata yield realistic road traffic statistics at the macroscopic level. We constructed a complex road traffic cellular automaton based on the literature to challenge array DBMS principles. For instance, each vehicle has several properties like vehicle length and vehicle speed. Our model has multiple lanes, road intersections, traffic lights, different vehicles' lengths, varying vehicles' speed, and complex vehicles' behavior. Now, we describe our model without referring to any array DBMS. Four main ingredients constitute cellular automata: the physical environment, cells states, cells neighborhoods, and local transition rules. We consider the entire road network as a 2D lattice, a 2D array. Each road consists of multiple lanes, 3 in our model without loss of generality. We took a traditional traffic cellular automaton grid that is used in state-of-the-art research, an artificial road map resembling the Manhattan grid, New York City. Vehicles can move west-east or south-north and change moving direction at a road intersection. A lattice cell state indicates an impossible path, a lane without a vehicle, a west-east or south-north vehicle with a non-negative speed, a road intersection, or traffic lights. We account for vehicles of different lengths. A vehicle occupies an integer number of maximum 3 consecutive cells. Vehicles are allowed to change lanes, for example, in order to overtake a slower moving vehicle. In our model, we locate traffic lights at the bottom left at each road intersection. Traffic lights are red for west-east vehicles and green for south-north vehicles or vice versa. In addition, traffic lights can be yellow for all vehicles. Cells change their states at discrete time steps, iterations. At each time step, a vehicle can stay in the same cell, no move, advance some cells forward, change its lane, the same road, or road at a road intersection. The maximum vehicle speed is 3 cells per time step. Traffic cellular automata evolve in time and space by applying rules to cells. A rule takes into account a cell's local neighborhood to take state transition decisions. Rules are applied to all lattice cells simultaneously. Drivers make decisions independently of each other in parallel, but obeying some generally accepted rules. All cells in a window of 11 by 11 cells constitute the local neighborhood of a cell, the cell itself 5 cells back and 5 cells forward. A rule must check a set of constraints before deciding on the state change. For example, a rule for the left lane change must check for too close or fast-moving vehicles on the left to avoid collisions. We use a one-dimensional model to advance a vehicle along the same lane. The model defines 4 rules applied sequentially to the speed s and position x of a vehicle at each time step. Rules 1 and 2, acceleration and braking, Rule 3, randomization, and Rule 4, movement. A left or right lane change means shifting a vehicle a cell left or right. Certain constraints must be met to make the left lane change possible for a vehicle. There should be no vehicle directly in the left cell, and the closest vehicle in the left lane behind our vehicle is at least 1 cell away. In our model, we allow a left lane change for a vehicle if another vehicle in front of ours is moving slower. The right lane change rules are the same. All lane changes are probabilistic. Vehicles apply an additional rule to account for traffic lights. If the nearest traffic lights on the road ahead are red or yellow, a vehicle sets its speed to 0. At a road intersection, in our model, a vehicle goes forward if it's not in an outer lane of a road. Otherwise, a south-north vehicle may randomly decide to go forward or turn right if it's in the rightmost lane. Before turning, a vehicle checks for sufficient space in the lane to the right. The same applies to west-east moving vehicles. Now we describe the holistic simulation workflow. The physical environment and cell states can be modeled as 2D arrays. We use these 2D arrays as input: tca.lane, tca.speed, and tca.length. tca.lane is a 2D array that codes the road grid with values -1, 0, 1, 2, and 3. We have already seen it. tca.speed and tca.length are initial vehicles' speeds and lengths. Initially, vehicles are scattered randomly on the grid. A vehicle of any length is modeled by a cell having its rear bumper. Note that we do not store vehicle positions explicitly, as they are implicitly coded by cell coordinates. We faced multiple design challenges to enable cellular automata simulations possible inside array DBMS related to iterative workloads, cellular automata transition rules, parallel execution, and other challenges. To overcome the challenges, we introduced novel array DBMS components. These include the first native UDF language for array DBMSs, novel convolution operator, proactive simulation plans, retiling strategy, array versioning, logs, virtual access, and others. A cellular automaton rule resembles a traditional convolution operator. However, a cellular automaton rule is much more complex. It's a procedure accounting for constraints and updating any cells within the neighborhood. To support cellular automata simulations, we introduce a new convolution operator for array DBMS. Unlike conventional convolution operators, our convolution operator supplies a kernel, several input windows, and allows a kernel to modify an arbitrary number of cells throughout multiple output windows. However, this requires no array retiling strategy. To compute a convolution kernel, users provide UDFs in Java. An array DBMS iterates over the input array forms read-only input and writable output windows, all equipped with helper functions. Most array DBMSs can run Python or C++ UDFs, but they are treated as black boxes that cannot be optimized by DBMSs. In addition, query languages and non-native UDFs are unable to organize iterations inherent to physical simulations. It's possible to run iterations query by query, but a query output must be completely materialized before running the next query. And looking ahead, optimizations are unavailable as the big picture is unclear. We present the first native array DBMS language for UDFs. Let us explore the UDF for traffic cellular automata simulations. Native UDFs consist of commands that have the syntax similar to command line tools. Most users are familiar with such syntax and hopefully you will find it easy to code UDFs. To retain the initial arrays, we start by copying tca.speed and tca.length to intermediate $speed and $length arrays which are subject to optimizations. For example, they mostly reside in RAM. The loop will be executed 100 times. The cal command runs a convolution operator that is supplied as a Java UDF. A Java file, it contains the specified method. Calc accepts and produces an arbitrary number of input and output arrays. The OT parameter specifies the output array type. Quantiles in and out distinguish between the in and out arrays as their number is not fixed. The override flag forces calc to delete the output arrays if they exist and create new output arrays with the same name. An iteration ends by appending new 2D arrays $speed and $length to 3D arrays speed_h and len_h along the virtual time axis. With strict formal definitions of array operations, compiler techniques, and our new extensions, we built execution plans for several iterations ahead, proactive simulation plans. In this way, we avoid redundant materialization on overheads of scheduling individual queries. This UDF looks small, but it is challenging to execute. For instance, during loop unrolling, the same array name appears several times. The last calc command deletes the current $speed array and creates a new array with the same name. As we're building a plan several steps ahead, we must be able to keep and address all arrays, deleted and new, and to read and write all of them simultaneously. Please learn more by reading the paper. Our work provides a number of future research and development opportunities. For example, load balancing strategies are required for irregularly distributed objects and input arrays. Efficient storage of sparse arrays would be beneficial. Currently, the tca.len array has only 5 distinct values stored uncompressed. Novel indexing techniques could allow skipping batches of missing values to avoid wasting iteration time. A database approach to physical simulations brings numerous benefits. Let us take ChronosDB as an example. It enables automatic parallelization, easy debugging, DBMS-like data management, and interactive visualization, to name a few. Currently, only ChronosDB supports both end-to-end parallel cellular automata simulations and DBMS-like simulation data management. Let us have a closer look at some of the benefits. Cellular automata rules may use other datasets. For example, digital elevation models, wind speed, or surface temperature. To illustrate this benefit, we added a rule: too low surface temperature may slow down a vehicle. Note that TCA.temperature array in the native array DBMS UDF. We used ChronosDB to prepare, ingest, resample, and slice Landsat 8 satellite data for surface temperature. ChronosDB partitions arrays into subarrays and runs the simulation independently on subarrays in parallel, managing all necessary data exchanges between them. It is easy to debug step-by-step Cellular Automata UDFs in Java used for cal commands. For example, in IntelliJ IDEA, just put tca.java in a module visible for the IDE. Its powerful debugger makes it easy to code UDFs, track Cellular Automata decisions, and explore convolution windows rendered by toString as ASCII 2D maps showing nearby vehicles' speeds, lengths, locations, and traffic lights. It's possible to archive, query, and compare simulation outputs. ChronosDB storage layer is built on top of raw files in standard formats. Simulation arrays tca.speed, .length, .lane, intermediate arrays, output 3D arrays are stored as full-fledged georeferenced GOT files, readily accessible to Python, GDAL, R, QuantumGIS, and other software. ChronosDB is also an HTTP server. Users can download any array via HTTP. We visualized simulation arrays in QuantumGIS, a free and popular GIS. It is possible to find these visualizations at the paper homepage. We showed that ChronosDB array DBMS can be used for end-to-end Cellular Automata simulations. The very fact of the possibility of an array DBMS application to end-to-end physical simulations is valuable. We believe this may inspire the related future work. Their support for Cellular Automata models can also be a step towards supporting even more general approaches like agent-based modeling. Finally, Cellular Automata models challenge array DBMSs, helping them to become more robust systems in general. Let us showcase one of the benefits of running the simulations inside array DBMS. ChronosDB provides array imagery via an open, popular web mapping protocol. Hence, in the ChronosDB web graphical interface, users can watch the modeling at work on an interactive web map. How vehicles move along the roads, queue at traffic lights, turn at road crossings, accelerate, brake, change lanes, and overtake each other. To our best knowledge, our work is the first to run end-to-end Cellular Automata simulations completely inside array DBMS. We enable array DBMS to simulate the physical world for the first time. Please learn more at the paper homepage and from the Open Access SIGMOD research paper. Thank you for your attention.